Hello again, my dear students, and welcome now to the second part with our atomic radiation chapter number 3 in the optical system course. If you remember, my dear students, we have dealt in the first part of this chapter with the assumptions or the probability associated with a two-level system. First of all, we have introduced the very basic assumptions. When an electron absorb a photon with an energy E2 minus E1 or greater, then this electron is absorbed and this photon is absorbed and the electron is moving from the E1 to the E2. And the vice versa process when the electron fall from E2 to E1 and a photon is emitted with an energy E2 minus E1. However, based on the Einstein approach, we have found that we have three main probabilities, not two. The first was named by spontaneous emission, where an electron moves from E1 to E2 and a photon is emitted with an energy E2 minus E1. However, I usually call this photon as an uncontrolled photon. What I mean by uncontrolled photon, that this photon has no granted energy, direction, polarity, or frequency. That's why we have nothing, maybe or direction. So you can never control this photon. Herein we start to write what's called rate equation to express the rate of variation with respect to time, of course, for the popularity in E2, which we call it N2, and the popularity of E1, which we call it N1. And as we are losing electron from E2 and gaining electron from E1, then the term dN2 by dt will be with a negative sign, where A21 represents the rate and N2 represents the total number of electrons or particles in level 2. The other assumption, which is again a basic assumption, which is the absorption assumption. Whenever a photon with an energy E2 minus E1 absorbed by an electron, then the electron will move. Accordingly, in this case, whenever you write the rate equation for the energy level number 2 by dN2 by dt, you will have a positive sign because the number of electrons increase in N2. And the rate for this, we call it B12. Again, N1 now is your stock. And as this process is a frequency dependent process, because you need not any photon will be absorbed, a photon with an energy E2 minus E1 or greater only will be absorbed. That's why we have this rho of mu, which is a frequency density function, to express the frequency dependent. And as expected, the rate equation for N1 will be negative to the rate equation of N2. Finally, we have this third genius assumption by Einstein, which we call as the stimulated emission assumption. In the stimulated emission assumption, we have a photon, and this photon is introduced to the system. However, this photon will not be absorbed by an electron from E1. What will happen that by the time this photon reaches the system, another photon will be emitted due to the falling of an electron from E2 to E1. And this photon, which is the emitted photon from the system, should be coherent with the previously inserted photon. That's why we call these two photons coupled or coherent photons. What do we mean by coherent photon is that these two photons should have the same direction, the same polarity, the same frequency, the same energy. They are equal and identical in everything. That's why we call them a coherent photons. If this happens, we call this process a stimulated emission process. And herein we write the rate equation by dN2 by dt equals to negative, because you are losing electron from E2, P21, which is the rate expressing this stimulated emission process, N2, your stock is N2, and rho mu, because again, this is a frequency dependent equation, because the frequency of the emitted photon should match the frequency of the incident photon. That's why there is a rho of mu function. Then we start to write a general rate equation to include all the coefficients. So we have three processes running simultaneously. We have the spontaneous emission process. We identify it as a spontaneous emission because this is the only process which is frequency independent, as you can see. We have an absorption process, which is a positive sign and frequency dependent. And we have the stimulated emission process, which is a negative sign and frequency dependent. And in order to make this equation mathematically more simple, we assume what we call the thermodynamic equilibrium condition. I mean, we assume that the dn2 by dt equals to dn1 by dt equals to 0. So that due to these three simultaneous processes, the number of electrons in N2 and N1 are kept constant. Accordingly, we can easily make some sort of mathematical management in order to reach this equation, which is N2 over N1, and this is the output, as you can see. Again, these all are some sort of flashback for what we did in part number 1. Then we start to use the other side, which what we call the Boltzmann statistics. Based on the Boltzmann statistics, we know that N2 over N1 equals to G2 over G1 e power minus H mu over KT. And then we start to equalize. Maybe you can refer to part number 1 if you need to know more about how we got this equation. We describe it in details in part number 1. Then we equalize this equation with this one. And using these two equations, we have concluded an equation to express rho of mu. And if you remember, my dear students, this rho of mu were already empirically formulated before when we are dealing with what we call the black body radiation. So we start to compare these two equations together in order to get a relation between the three coefficients introduced by Einstein. And in this case, we found that B12 times G2 equals P21 times G1, and A21 over B21 equal to this term, which is 8 by n cube H mu cube over C cube, where n is defined as the refractive index of the material of the medium, mu of the frequency, of course, and C is the speed of light. So this is the relation, and as you can see, this is one of the very tricky things, my dear students, that this equation does not include n, because here we consider a black body radiation in air, so n equals to 1. However, generally you can include n for any medium of propagation. So this was the termination of part number 1, if you remember. Now we have a rate equation, and also now we have the energy or the relation between the coefficients, the three coefficients introduced by Einstein. And if you remember, I told you that one of the genius points of these derivations that whenever we start to express the three processes introduced by Einstein, the spontaneous, the stimulated emissions, and the absorption, we consider them from the first principle as three uncorrelated processes. However, using this mathematical derivation by Einstein, we can see that these three processes are correlated processes because we simply link the coefficients of these processes. Now, after these three assumptions, we can say that, okay, this is three good assumptions where we can use to express a two-level system. However, in the realistic case, this two-level assumption is not very accurate. Why? We have to return back to our semiconductor devices course. Whenever we introduce what we call the band theory, if you remember. And in this theory, I told you that in order to deal with the energy levels as discrete energy level, this is what we call the isolated atom model. However, in a material model, we no longer have a discrete energy level, and we have what we call, if you remember, the bands, the valency band and the condition bands and so on. So it is more accurate to deal with this energy level in terms of bands, not energy level. But the question is, what is the difference between having an energy level and having an energy band? This is what we are going to discuss in the next slide. Okay, so now our new model will not include only two energy levels. It will include something like that. So instead of having one energy level, let's say that this energy level is turned to band. And if you remember, the definition of a band is a series of successive energy levels. So for example, we assume that this number 2 level is expanded to be a band, including, for example, 3 levels. One is centered, and the other 2 is somehow shifted. Let's say delta mu with respect to the one. So for example, we have E2 plus delta mu, and E2 minus delta mu. So these are the 2 energy levels. So of course, it should be E2 plus H delta mu and E2 minus H delta mu. And similarly, in band number 1, we have 3 levels. So this is the central level, and then we have 2 other levels. Okay, but let's now ask us a question. What is the difference between dealing with 2 energy level system or a 2 energy band system? The answer actually is very easy, and I expect that you can easily guess this answer. Whenever you have 2 energy level, then once an electron falls from energy level E2 to energy level E1, you have a single probability that the emitted photon will have an energy H mu equals to E2 minus E1. No other option, because you only have 2 energy levels. So the emitted photon will have an energy equals to the energy difference between these 2 energy levels. However, whenever you have this energy band structure, then you start to have different probabilities, because of course there is still a probability that there is an electron in energy level E2 and drops to energy level E1, then it will emit a photon equals to E2 minus E1, or what's called here mu2 minus mu1. Of course, mu and the E are proportional. However, we still have other probabilities. For example, this photon was in an energy E2 minus delta E and will fall to an energy level E1 plus delta E. Then the emitted energy level, the emitted photon will have an energy smaller than E2 minus E1, because simply the energy gap here is smaller. So the emitted photon will have a smaller energy or a smaller frequency. Again, another probability to have an electron here, and then this electron will drop there to the lowest bottom level in the system. Accordingly, the emitted photon will have an energy or a frequency greater than E21 or mu21. So it's simply a game of probability. Now you have different probabilities. However, in the hypothetical system, where you have only 2 energy levels, you have only a single probability. That's why we start to introduce what's called the line width function, which is actually a critical point in this chapter. The line width function is a function that expresses the probability of the emitted photon versus the frequency or energy. I'm quite sure that you know that energy and the frequency are the same meaning, because energy equals Planck's constant and frequency. So you can have this x-axis frequency, or you can have this x-axis energy. And by the way, in the end of this chapter, we are going to solve an example, a solved example, where we will see that this x-axis can be other parameters, not only energy and frequency. But let's now start with the easiest one, to have this x-axis as a frequency or energy, and this is a probability to find to emit an electron. As expected, the highest probability will be still mu21. However, it's no longer it's no longer a single probability. We have a probability density function, or what we call a line shape function, that express different probabilities of an emitted photon based on different cases, as we see. And knowing that this is a probability density function, we can easily say that the integration under this curve will be equals to 1, because the integration, as you know, is directly the summation, and whenever we have a probabilities, the summation of these probabilities should tends to 1. That's why we have to say that the integration under the, or the area under this curve, which is of course the integration, should be equals to. So now this is a line shape function. What we are going to do now, my dear students, is that we are going to introduce this line shape function into our rate equation. In this rate equation, this is the old version of the rate equation where we have only two energy levels. So we have a single probability of frequency. However, in the realistic case, whenever we have a band, not a level, we have to include the probabilities or this line shape function. So let's now start to embed this g of mu function into our equation and see what will happen with this equation. So let's do it. Okay, perfect. Let's start with the old version. The old version of the equation was as following. We have dn, not so good for writing. Let's do it with this one. dn2 by dt, which is the rate of variation of the popularity level number 2, equals to. The first, we have a spontaneous emission curve parameter, which is minus A21 times N2. And then we have plus the absorption term, which is B12 N1 rho of mu. And then we have this third stimulated emission term, which is B21 N1, B21 N2, again rho of mu. This is the old version of a rate equation. Now, what we are seeking for is to introduce the new line of shape function to this equation. So simply, I will add this integration from 0 to infinity g of mu dash d mu dash. And similarly here, this is integration, and this is g of mu dash d mu dash. And similarly here, g of mu dash d mu dash. So now this will be the general form of the equation after including the line shape function. However, you can easily say that this term has no meaning because now in this spontaneous emission, you don't have any frequency dependent parameter. You don't have rho mu. So you are just integrating g of mu d mu. And as we said, this is a probability density function. So the integration of this will lead to 1. So in the spontaneous emission case, the effect of the line weights function has no meaning. And actually, this makes sense because in the line in the line shape or in the band structure, the issue is that you can emit a photon with different frequency. And as we previously described, in the spontaneous emission, there is no grant or there is no control about the frequency of the emitted photon. So it does matter if it's mu1 or any other different frequency. That's why it shouldn't be included. So in this term, we will not have this line shape function. And we will still have this line shape function in the other two terms. Here in the absorption term, because we have this rho mu, and here in the spontaneous term, stimulated emission term, as we have the rho mu. Okay. So in order to continue solving this equation, we have to know, we already have, by the way, a relation between these three coefficients, if you remember. We have already concluded this relation, and we have this linking between these three coefficients. So herein we have some data to insert. So we can, for example, replace B21 and B12 with an equation in terms of A21, and we can write the equation. This is easy, and we will do it. However, we have nothing about this rho of mu. What is this rho of mu? Or how we can express this rho of mu? So let's now start to think a bit about what is this density function. Okay. So I will return back to my presentation slides again. Perfect. And let's now have the pointer. So what I did, okay, I think, yes. What I did here, as you can see, is that I just substitute with this integrations, as you can see, and we say that this integration has no meaning. It will be equals to 1, so we can easily remove. However, we will still have these two integrations. And the question is, what is rho mu? So in order to answer the question, what is rho mu, we have first to think from where we introduce this rho mu. This rho mu has been introduced in two cases. First, we have introduced this rho mu in the case we have an absorption, because we say that we have a frequency dependent process. The source should have a frequency which is equals to E2 minus E1 or greater, so that the photon can be absorbed by an electron. In the second case, we also introduce rho mu because we say that the output photon should match the frequency, the phase, the polarity, and the direction of the incident photon. So from these two examples, you can conclude that this rho mu appears whenever you have an incident photon, because this is the common between this stimulated emission process and this absorption process. In these two processes, we have an incident light. However, in the spontaneous emission processes, we don't have an incident light. So simply, rho mu describes the case where we have an incident light directed to the your material. Either it will lead to an absorption, or it may lead to a stimulated emission. Okay, so what we can do now is that we can replace our rho mu with the density of our light source, our incident light source to the material. So we have to define what type of energy we are incident, what type of optical energy, what type of light source we are incident to our material. Herein, we are going to describe two extreme cases. The first case we have already discovered before, which is the black body radiation, if you remember. In the beginning of the lecture, or in the beginning of the chapter, we have introduced together that in a black body radiation, we have a spectrum density, looks like that. And this is a temperature dependent, if you remember. So whenever you increase the temperature, the peak is shifted from the infrared till it's reached the visible and goes to the ultraviolet. So these are different curves expressing the density function for different materials, or sorry, for different temperatures. Here we have what we call a broad spectrum. What I mean by a broad spectrum is that this spectrum include too many or a wide range of frequencies, as you can see, or a wide range of wavelengths. So this is a broad curve, a broadband curve. That's why we call this as an extreme case, like what the energy transferred to us. The energy is a very broadband source. And the sun is a very broadband source. The sun transmits ultraviolet, visible, and infrared photons. It's a very wide source. The other extreme, my dear students, is what we call lasers. The lasers are a monochromatic sources that transmit photons in a single wavelength or a single frequency. So these are the two extremes. Something very, very, very narrow band, actually it's zero band, which is the coherent laser, and the other, which is a very wide band, which is the black body. In between, of course, we have a very huge amount of light sources, including different artificial light sources like LEDs and xenon lamps and halogen lamps and so on. But in order to, actually, we will select laser. We will select lasers for two main reasons. First, because if you remember chapter number 1 and chapter number 2, we usually said that we are interested in lasers because lasers are our targeted modulators or carriers in the modulation systems. Second, because the inclusion of a laser will make the equation more easy from a mathematical point of view. This laser can be easily expressed as a delta Dirac function, if you remember this delta Dirac function. So what you are going simply to do is you are going to replace the equation you can see here in my whiteboard. And in each row of mu, we are going to insert this row mu, which is a constant, times a delta Dirac function shifted at a wavelength or a frequency indicating the wavelength of the or the frequency of the laser. That's all. So you just replace this with a delta Dirac function. Accordingly, it will be to some extent easy to go to this equation and replace it with a delta Dirac function. Okay, so let's now return to our whiteboard, and now this is our equation. No longer the G of mu in the spontaneous curve. What we are going to do now, my dear students, is just we are going to replace this rho mu with a constant multiplied by a delta Dirac function. That's why we have this expression. So let's do it together. So we will have our equation. dN2 by dt equals minus A21 N2. It's typically the same. Nothing has happened. Plus B12 times integration from 0 to infinity. Then I will going to replace rho mu by rho mu delta mu minus mu dash G mu dash d mu dash minus B21, and of course, I'm sorry, here I have N1 also. I'm sorry, here we have N1. B21 N2 integration from 0 to infinity rho mu delta mu minus mu dash G of mu dash d mu dash. If you are a strong student, outstanding student in communications and signals systems, you will remember this integration. This is a convolution integration with a delta Dirac. If you remember, this is actually the integration representing the modulation system. Whenever you have a message convoluted in the time domain with a carrier, then the message frequency shifted from a baseband to a passband. This is just an analogy, mathematical analogy, but however, of course, this is not a modulation. So this is typically the same. You have an equation that represents the shifting of G of mu toward the delta mu. So the output of this will be simply rho mu, which is a constant, times G of mu. So you can rewrite the equation in this form: dN2 by dt equals negative A21 N2 plus B12 N1 rho of mu G of mu plus مش plus, I'm sorry, minus P21 N2 rho of mu G of mu. And this is another rate equation. Now you can do the replacements. We already have some equations. We have already reached before, which links between A21 and B12, and between B12 and B21. So you can just kick out these two constants, B21 and B12, and write them in terms of A21. So let's do it. Let's do it over our presentation slide. So now this is our laser pointer. So now this is the equation we have just reached. So this is the spontaneous term, this is the absorption term, and this is the stimulated term. And we have already concluded that B12 equals to B21 G2 over G1, and B21 equals to C cubed 8 by N cube H mu cube A21. So you can just replace this in terms of A21. And now we can introduce this rho mu, or the density, as the normalized intensity. So we are just normalizing the intensity with respect to speed. The intensity is I mu, and the speed, of course, is C over N, where C is the speed of light and N is the refractive index of the material. So this is just a substituting. So I'm going to substitute these three terms here in this equation. So I will get this general term. Let's start to understand this term. I believe you can do it very easy in your home, or you can follow the script. I already make it step by step in the script if you would like. So herein, dN2 by dt, due to the radiative, it's a general dN2 by dt due to the three simultaneous processes, spontaneous, stimulated, and absorption. So this dN2 by dt is equals to, this is usually a very easily recognized spontaneous emission. Why I know this is a spontaneous emission? Because simply it's a frequency independent term. This is the only frequency independent term in the equation. Then we have minus this big term, which is A21 lambda squared 8 by N squared G of mu times I of mu H of mu times N2 minus N1 G2 by G1. If I ask you, please, my dear students, which of these terms represents the absorption and which of these terms represents the stimulated emission, you can easily recognize that this term with a positive, with a negative sign represents the stimulated emission, because the stimulated emission means that you have electrons falling from E2 to E1. So the number of electrons in E2 decrease. That's why it's a negative. However, the absorption, which increment or increase the number of particles in E2, will have a positive sign, negative, negative, positive. So this term represents the absorption term. Okay, but let's now for some while, let's now start focusing on this in bracket term. A21 lambda square 8 by N square G of mu. So what about this term? As you can easily know, that what I'm asking you to do is to determine the unit of this term. What is the unit of this term? It's A21 lambda square over 8 by N square G of mu. Let's start thinking about that. Okay, so the term we are talking about is A21 lambda square 8 by N square times G of mu. This is the targeted term. Let's see, what is A21? A21 represents the rate of the falling electrons due to the spontaneous emission. If you remember, we first introduced when we say that we have an electron here, and this electron will fall. We have, yes, an electron here, and this fall will electron like this, and it will emit a photon, H mu. So we say that dN2 by dt equals to negative A21 N2. Easily from this equation, here you have N2, which is a density, maybe centimeter per minus 3. over time. So this A2 is a rate. Accordingly, it should have a second minus 1 unit. So the unit of A21 is second minus 1, which is a rate. Any rate by default is 1 over time. Then lambda square, of course, will have a distance square unit, meter square or centimeter square or whatever. 8 by are constants and the refractive index, which is a dimensionless. G of mu. What is G of mu? Please remember, G of mu is the line shape function. So, do the line shape function, or does the line shape function has a unit? Let's see. We say that, if you remember, if this mu, this is G of mu. Perfectly. So, is this G of mu, which is a probability, does probability have a unit? Let's see. You told me that integration of from 0 to infinity of G of mu d mu should be equals to 1. So the integration, which is represents the area under the curve, means what? Means that you are multiplying the y-axis value times the x-axis value. Accordingly, if you multiply the y-axis value by the x-axis value, the output should be equals to 1, which is a dimensionless, of course. So, in order to multiply two factors together, and the output is a dimensionless, that means that these two factors should have a reciprocal unit. So, if the unit of the frequency is second minus 1, which is hertz, that means that this G of mu should definitely have a unit of second. So that when you multiply second times second minus 1, you will get a dimensionless unit. Accordingly, this G of mu will have a unit of second minus 1. And please take care. This is a very tricky part in our chapter, because once I plot to you this G, not a function of mu, for example, a function of energy, that means that its reciprocal unit will not be second minus 1. It will be electron volt minus 1. If this unit, if this x-axis is lambda, then the corresponding G on the y-axis will not be second minus 1. It will be centimeter per minus 1. So usually this G will have a unit which is 1 over the unit of the x, not second minus 1 by default. It depends on what is in the x. So you have to check what is in the x, and then you can conclude the unit of the y-axis. So in case it's G of mu, which is our case, it will have a unit of second minus 1. Now you have, this is a dimensionless, this is second minus 1, this is second. I'm sorry, this is second, not second minus 1. I'm sorry, this is second. So this is second minus 1. So they will be cancelled by each other. And then this term generally will have a unit of meter square area. So what we are going to do, my dear students, is that we are going to have this parameter, which is A21 lambda square 8 pi n square G of mu. We are going to call this the stimulated emission cross-section. We call it the stimulated emission cross-section because simply this is associated to this term N2, which represents the stimulated emission, and sigma, which will become a very famous term for our course, will have a unit of meter square. So you can generally rewrite this equation saying that dN2 by dt equals to negative A21 N2, which is a spontaneous term, minus sigma, which is this cross-section, I mu over H mu, N2, which represents the stimulated emission, minus N1 G2 over G1, which represents the absorption. And this become what we can call the general rate equation for a two-level systems. This will be the termination for part number 2. In part number 3, we will start to use this equation in order to determine something very critical, which is the critical condition for light amplification. So the next part, most probably will be the last part of this chapter, is one of the very important parts in our course. And maybe by the end of this part, or maybe in part number 4, we are going to solve a complete solved example in this chapter. Thank you very much, my dear students, and see you in the next chapter. In the next part number 3. Thank you very much.